Don't cause the loss until it's gone. In the sense that we used to win.
I just wanted to ask you something. Do you meet people who help your GPs with at this stage for their projects or data analysis?
Yes. There isn't a specific need to that. However, I wanted to look at it.
A whole bunch of didn't get through them, but sold it to his colleagues. Month in, month out. And then that's the same for so many colleagues.
Then you can't take a photo.
I'm in the School of Natural Sciences.
Natural Sciences. And that's E.Klapper.
E.Klapper, Kent, PPA.
It's not blurry. There you go. At ken.ec.uk. Thank you very much, Peter.
My
never
pleasure.
know where these conversations will go.
I once got a job in Malaysia from a conversation like that. Have a lovely day. Sorry, I'm in the way.
And I was like, that can work.
Good.
Yes. Thank you.
I don't know.
Yeah, we get all the sample through for biology. Yeah. I think that we do like a biomarker. No, definitely not.
Honestly, I was eventually using chemistry because I felt really bad because you were in like general public with all biologists and biology.
Yeah,
That
yeah, I'm not chemistry background here. I'm forced into biology.
I mean, it's just because if you say chemistry, you chemistry background. It's good, isn't it? Honestly, it's good.
Yeah.
Well, okay. So what do you
Well, it's not management. Yeah.
Would you have a lunch? Think off to the pub and
Yeah, it's quite interesting to learn more in life.
like the endpoints essentially?
Yeah. Yeah, we got the sample through and test the endpoints and then send them later. So doing sample analysis at the minute, but I told you No, it's the final last year, so we were just
Oh, okay.
starting from last week. Yeah, it's stuff. It's actually been a lot more.
Yeah, I bet. Maybe. Maybe you just sound like you know which structures are. What are you talking about? I think you started off
Numbers have gone down a little bit. Maybe it's. Is it sunny?
Not really.
Oh, really? Oh. So they don't really have an excuse. Oh. Okay. Well, let's crack on because I promised people that we are out a little bit earlier than 3. I hope you don't mind. No? Good. Okay. So thank you very much for coming back to this second session today. And in this session, I want to start with telling you something really sad. It's almost heartbreaking. Don't cry, okay? What we have done so far with all this data calculation, means, variance, visualizing, it's lovely, but utterly pointless. Yeah, it's sad. Because, let's face it, if I measure the height of 5 people, I measure the height of Alex, Mohammed, Ali, Charlie, Ify, was 5. And I measure it and record it. Who cares? Nobody. Nobody gives a flying flamingo about the data, right? Looks great, yeah, you've measured them, but what's the point, right? Now, all this explorative data analysis that we have done is nice for the books, and it's, shows that you can do measurements. But in reality, it doesn't mean anything. Because it is a sort of a snapshot, and things might change. And nobody is really interested in the height of these 5 people. So why the hell do we do statistics? Well, the answer is we try to make life easier for us by answering. We want to answer big questions. But we can't answer them directly. And therefore, we need to take some sort of small-scale measurements, samples. So, for example, I want to know, for one reason or another, I want to know what is the average height of a student in the UK, right? That's the whole population of students in the UK. Of course, I can't measure everybody. I can't go around and measure every student. I can't go into the high street as, are you a student? Yes? Okay, can I measure you? And they go like, the guy is loopy, right? Why? So what we usually do is we use statistics, we use our data, and we work from, say, a small sample, and we try to make some conclusions about the whole population. And answer some questions. Of course, we have to make sure that these samples come from the population that we are looking at. I mean, there is no point in, for example, measuring the weight of 10 cats if I was interested in the average weight of dogs. That makes sense. So sample has to come from the population. Ideally, has to be representative. And what we are going to do in the rest of the time is really we are trying to answer the question, how can we use sort of small-scale samples in order to make conclusions, make inferences about big populations. That is what statistics is all about. So instead of measuring people and say, hey, that's great, let's go to the pub. No, we want to use these data to answer bigger questions. And that is what we call inferential statistics. What we have done this morning and yesterday, that was descriptive statistics. And we also explored the data, looked at the data. But what we are doing now is we want to make these inferences. And the first thing that we need to sort of introduce is something really disgusting. I give you an example what I mean. Let's say I take a sample of 5 people here, 1, 2, 3, 4, 5, and measure their height. So height. Sample 1. And I say, okay, I can calculate the mean of the sample. So a mean of sample 1. And we know how we calculate the mean. And we say, well, if this is a true representative sample of the population, then this mean of the sample is probably a good representation of the mean of the population. So I take the mean, divide by 5, or add them all up, divide by 5, and get a number 175 centimeter, and say, because the sample mean is 175 centimeters, my conclusion is most likely the sample is representative and the population mean is also 175. Yeah, makes sense. It's a reasonable approach. And that is what we very often do. We take what is called sample statistics, and we try to estimate what is called population parameters. In this case, the mean of the population. And in order to distinguish between these two things, the sample statistics, the mean of the sample, and the population parameter, statisticians use slightly different notations. Everything that refers to the population parameter is usually given in Greek letters. So the population parameter for the entire population would be abbreviated by the Greek letter mu. Whereas the sample mean, in this case, would be abbreviated with something that's even more horrible on the keyboard because you can't find it. It is an X with a little bar on top of it, which is called X bar. You can't find that on the keyboard. There's one of the really special mathematical characters. Now, in this case, this sample mean, we say is the same as the population mean. We assume it's the same. Yeah? For the variance, we said the variance is sigma square. For the same thing, for the sample statistics, is S square. It's exactly the same thing. The Greek indicates we are talking about the whole population. The, well, not Greek letters indicate we are talking about samples. So that's, please bear that in mind when you, for example, see something in the literature. Okay, so I've taken 5 people, sample, mean X bar equals 175 centimeters. My conclusion is the population mean is also 175 centimeters. And because, today is Wednesday, the decision is, why don't I take another sample? Doesn't have to be the same people, of course. We'll just take people at random. 1, 2, 3, 4, 5. So I take another sample mean. So that's sample mean 2. And I've got X bar 1 and I've got X bar 2. Right? So X bar 1 was 175 centimeters. X bar 2 is, do you think that the mean of the second sample will be the same? Will also be 175 centimeters.
It should be, it might not be exact.
It should be.
But it should be similar.
It should be similar. So you said
I said it wouldn't, yeah, it wouldn't be the same.
it wouldn't be the same. It should be close, yeah, but it won't be the same. That leaves us with a little problem, doesn't it? Let's say this is 178 centimeters. That's a bit, Which one should we believe? Which mean? The population mean can't be 2 values, because if I measure the entire population, I will come up with 1 mean. End of story. Well, which one should I be? Should I believe the 175? Should I believe the 178? Okay, we take another mean, right? This one, it is 173. Bless you. 173. Which one? Help me out. Which one shall I take for my estimate of the population? Which one is right? Sorry? I can take it.
A mean of
the mean of the means. That's a good idea. But, you see, this is a problem because for each sample, I get a different answer. Does anyone know what this phenomenon is called? It's called, no, not yet. Not yet. This is actually called sampling error. I hate this term because it sort of infers that we made a mistake. Error, it's not a good thing. But we haven't made a mistake. For Pete's sake, we will be able to calculate the mean of 5 heights, right? So there's no mistake in it. I like to see it as sampling uncertainty because, yes, we get the right numbers, but they're always different depending on the sample. And I like to think of sampling error a little bit like herpes. Whenever you take a sample, you have sampling error. Like herpes. You've got herpes. You've got the virus. End of discussion, right? Deal with it. Everybody has herpes. Cold sores, mouth ulcers. 85% of the population have the herpes virus. You can't do anything about it. Sampling error is there. Every time you take a sample, you will have some sampling error. So what does that mean? Does that mean that basically our entire statistics sort of is totally effed? Can't do anything? We can't make any judgment about the population mean? Well, not necessarily. So we have these different sample means. How can we say something about the population mean? Be creative. Come up with an idea where we can still make a judgment about the population mean. What could we do? You said we could do the mean of the means. Yeah, that's a good idea. But sort of in a slightly different context, what we could do is, we say, the population mean, so it is an estimate, estimated population mean, because we probably will never know what the true population mean is. It's always an estimate. This mu, population mean, don't want the ruler, is probably the sample mean that was our previous thing, but we know it's not exactly the same. Now we say just simply plus or minus a bit. I know it's terribly scientific, right? We just simply say, okay, the true population mean is 175 centimeter plus or minus a bit. In this case, we most likely have 178. If the true population mean is 178, yeah, 175 plus minus a bit. If we make this a bit big enough, then the true population mean is included. Or if it is the true population mean is 172, and we make this a bit large enough, then 175 minus a bit, if it is large enough, it will contain the true population mean. Yeah? So that gives us an idea what the population mean is. It doesn't tell us exactly what it is, but we will never have a way of finding exactly what it will be. This is as good as it gets. So what we end up with is basically we have the mean, and what we can do is we can say, right, this is our bit plus or minus a bit. Now, technically, people don't write a bit. They actually write margin of error. So this would be a margin of error, and this would also be the margin of error. OE, and it's usually abbreviated as MOE, margin of error. This part here, this one here, is the lower bound. This one here is the upper bound. And the whole range here, does anyone know what this is called? That is the confidence interval. You're absolutely right. This is the confidence interval, the whole thing. We've got a lower bound of the confidence interval and an upper bound of the confidence interval. If we only knew what the margin of error was, then we could easily find that out. So I guess probably, well, I'm quite sure that it's probably plus minus 20 centimeters. It's sort of, this confidence interval is actually a range where I say, I'm pretty sure that the true population mean is located in this range. Yeah, that is basically what a confidence interval tells you. In this case here, when we are working with continuous data under certain conditions, it's symmetrical, so plus or minus this margin of error, but it doesn't have to be symmetrical, as we will see. There are confidence intervals that are not symmetrical. Okay, how do we calculate a confidence interval? Next problem. Let's think about it. What does the confidence interval depend on? Have I got that somewhere? Yeah, I think I do. Copy. So the confidence interval depends on a number of factors. The first one, we just park that for a moment. Yeah, this is how confident we want to be, because we need to think in a little bit of a different way about this. So let's park that. The confidence interval depends on the data type. Are the data continuous, or do we have discrete data? Let's park that as well. The distribution, I will say something about that in a moment. Of course, the confidence interval depends on the variability in the population. For example, if everybody was exactly the same height of 175 centimeters, and I knew that, if every person in the whole world was exactly 175 centimeters, then I could say my estimated population mean is 175 centimeters plus minus 0 centimeters, because everybody has the same height, right? So there's no variability, and my confidence interval would be very small. But if I had, for example, if I knew that I had very small people, very tall people, huge variability, then I would make this confidence interval larger, because I don't know for sure where people are. So variability in the population is very important. How do we measure variability? What is a measure of variability?
Standard deviation.
Absolutely right. So we want the standard deviation. That's a very good measure of variability. And we have to come back to that, because we immediately run into another problem. And last but not least, our confidence interval depends on the sample size. What do I mean by that? If I just take a handful of people, there is a decent chance that just by sheer dumb luck, I got 5 fairly tall people, or very small people. But if I take 100 people, doesn't matter if there are a few tall, if there are a few small people, they will sort of average themselves out. So with a large sample size, I can be fairly sure that this is more representative of the population than a small sample size. This is actually called the law of large numbers. Okay? So usually people say you need at least 30 as a good sample size. There's no reason actually why you should choose 30. Can it be 29? Can it be 28? Yeah, it can be. But the more you have, the better it is, because then any extreme values will be compensated, really, and it will give you a sort of a much better idea what the population is. Now, I said there is another problem here with the standard deviation. We said for our data, we can calculate the standard deviation. And this was the square root of the squares squared divided by the number of observations that we had. Yeah, that is what we did yesterday, and what I repeated today. Now what you see is these are the data, and we treat the data basically as our population when we've calculated it. This was our population of the data. This is all that we had. But if we use the data, so that was the population, really, from our observations. We treated it as a population. But if we treat the data as representing the population, we are working with a sample. So from sample, so we take the measurements and say that is now our sample, and from that we want to make an inference to the population. We only take a small group of people. But the problem is we don't know the variability of the population. We have only the small group of people, and we are trying to figure out what is the population variability. Now, the question is, will this population variability be bigger or smaller than the sample? Now, what we see here in this diagram is, here is our variability, basically, for sample 2. And the variability for the population is larger. It's always larger than the sample. Yeah? How do we deal with that? That it's always larger than the sample. We need to basically make this guy here larger. We need to write our population standard deviation as estimated from the sample. We still can use a similar equation. But in this case, we are working basically with the sample. This is just to estimate the population. Xi, our observation. This time, we take the sample mean, square it. And now we need to make that a little bit larger than our sigma. The way you do that is you don't divide by n, by the number of observations that you have. You divide by something slightly smaller, n minus 1. That is a standard deviation, an estimate for the variability of the population coming from the sample. And what you see is there are two different standard deviations now that we have. One says, right, these are our data. We describe our data. This is only for describing data. And I told you this is standard def dot p. This one here is only for estimating standard deviation or variability. Let's call it variability. Only for estimating the variability from sample. And in Excel, it is standard def.s. That's why you have two standard deviations and two variances. Variance would be var.p, var.s. They are looking at very different things. In one case, it is only for describing the data, that's the P, and for the S, the S is when we want to make inferences, because this little s, the standard deviation, is slightly bigger than the sigma, because we divide by something slightly smaller. Now, if you look at it from a slightly different point of view, if we have 1,000 observations, 1,000 measurements of people, so our n equals 1,000, then it doesn't really matter whether we divide by n, by 1,000, or by 999. The numerator will be pretty much the same, and we divide 1,999. Big observation numbers, doesn't make any difference. But if we have only, let's say, 3 observations in total, then we divide by 3 here, whereas here we divide by 3 minus 1 equals 2. So in a way, this takes into account what I said about large numbers. The more observations we have, the more information we have about the population, and the more information we have about the variability of the population. So that is this S thing, the standard deviation. So when we are working towards finding the confidence interval, we work with this S and not with the sigma, because that's an estimate for the variability. What do I mean by distribution of the population? Right, distribution of population is a rather interesting thing, because we don't know what the population actually looks like. If we are looking for, let's say, height, then there is a pretty good chance that the population follows what is called a normal distribution. You're all familiar with the normal distribution? Yes, sort of. Yeah, normal distribution. Normal distribution, if we plot that, looks like that. Yeah? So here we've got there, for example, the height of people in centimeters or whatever. And what this basically says is we could have here frequency, how often something happens, or a probability that we find people like that. So probability, whatever we want to plot here. What it basically says is we have a few people who are small. We have a few people who are very tall. But most of them are sort of in this middle range here. Here we would have a mode. That's the one that we have most. And that would also be our mean here. And that is a typical bell-shaped curve. You have all seen these bell-shaped curves, yeah? It's also called a Gaussian curve. And bell-shaped Gaussian normal distribution. So that could happen in the population. Population could also be slightly different. It could be skewed. If I look at, for example, something totally different, if I look at how long people stay in hospital on average, it would not be such a Gaussian curve. It would be perhaps a curve that looks slightly different, that might look like something like that. Stay in hospital, or days in hospital. Most people will get out fairly quickly. Either way, only a few people will stay very long. So this is not a normal distributed curve. So our population could be like that. Or population could also be normal distributed, where we have something like that. Could be normal. Or, sorry, it could be uniform. There's no difference. So population can come in all different shapes and forms. If we have discrete data, now with discrete data, it gets really interesting. When we actually look at the whole days that a person stays in hospital, it would look like that. There is no sort of no line through it because they stay either 1 day or 2 days or 3 days, but we don't count anything in between. So for discrete data, these population distributions might look totally different. Yeah? So that's what I mean by it depends on the population distribution. Now, for the time being, we are looking at this normal distribution, and the normal distribution only applies to continuous data. Only if the data are continuous, we can work with a normal distribution. If the data are discrete, we cannot work with a normal distribution because it's totally different. And of course, the normal distribution has a few other quirks. It's not just any bell-shaped curve. We could, for example, define a range for this, for the x-axis. We can say, for example, we might say here is +1 standard deviation, and here is -1 standard deviation in the population. Yeah, we don't know the standard deviation, we try to estimate it. And it turns out that a specific of the normal distribution is that if we look at the data, here, between -1 standard deviation and +1 standard deviation, it has a fixed number of percentage of the data that are included in this shaded area. Does anyone know? 68%, you're absolutely right. So 68% of the data are actually located in this range of plus sigma and minus sigma. Yeah? If we extend that to -2 sigma and +2 sigma, let's take a different color. So that's this one here, the green one. Do you know how much this is?
I can't remember. Is it close to 6 or something like that?
This is actually, all the green one is 95%. Yeah? 95% of the data are included in that. And we could even go further. We could go to, say, 3. Three standard deviations. This would be 99.7% of the data are included in the red one. Basically, this normal distribution goes from -infinity to +infinity. And only in this very large range from negative to positive infinity, we will have all the data in it. Well, most of the data will be within the -2 +2 sigma range. Yeah? And lots of traits are following this normal distribution. For example, IQ. Human IQ is, you measure that with these IQ tests that you sometimes find on Facebook. Have you seen them? You're not using Facebook, right? Only old people use Facebook. That's what my kids told me. That Dad is using Facebook. God, he's so old. Where you can measure your IQ, these IQ tests are actually designed to follow a normal distribution with a mean of 100. So the mean is 100, and the standard deviation is actually 15. So 95% of the population would be between 70, that's the 2 times 15 on the negative side. 100 minus 30 is 70, and 130. I mean, if you are below 70, you are probably as intelligent as 250 grams steamed broccoli. Or you are a politician. Oh, sorry, I didn't. Did I say that? No, I didn't say that, right? And someone asked me recently, do you know how intelligent you are? And I said, I have no idea. What do you think? How intelligent are you? I said, I'm probably between 70 and 130. Oh, how do you know that? Well, 95% of the population is there. So, and I'm pretty normal, you know, well, not according to my wife, but 100 and that's probably in there. So that's a typical characteristic of the normal distribution, that we have these areas. Typical feature, normal distribution. Not every population actually is normal distributed, but most of them, there is a good chance that they are. Right, now, let's turn this on the head, the whole thing that we have done so far with the confidence interval. We haven't calculated anything yet because we are still missing something. And that was the first point, that I sort of parked. Why has that moved? How confident we want to be. What do I mean by this point? Yeah, here it is. How confident we want to be in our judgment. We've done all the other things. And that goes into a little bit of decision mathematics, which is a very interesting topic in mathematics. And just to give you an idea of what I mean is, let's say we have a sample. So here we've got 175 centimeter, that's our X bar. And we think that this sample was taken from a population, and the population mean of that is 190 centimeters. Apparently quite tall people there. Now, question is, we need to make a decision. Do we believe that this sample comes from this population? Do we believe that this tiny sample that we have with a mean of 175 centimeters actually is taken from the large population of 190 centimeters? Do we believe that? What's your view? Do you believe that they come from the same population? That it comes from that population?
How big the sample is?
Sorry?
How big the sample is?
How big the sample is? Let's say 10. I don't make it easy for you, right?
It could be.
It could be. What do you think?
It's not a very good sample size, no. But I mean, it's not a million miles away.
It's not a million miles away. We have to make a decision. You can't sit on the fence, because somebody told me that if you sit on the fence, it hurts, especially when you are a bloke. Okay, we need to make a decision. Of course, we can be wrong in our decision, but at least we've made a decision. And in order to introduce you to this concept, I have asked one of you to help me a little bit. Shannon, are you still up for it? Yeah, thank you very much. Big applause. Thank you. Because something absolutely horrible happened earlier. I left the room and left my chocolates here. Right? And when I came back, the chocolates were empty. So somebody must have stolen my chocolates. This is a heinous crime, and the person needs to be punished severely. Right? Absolutely. By the way, do you like chocolate?
Yeah, I'm
Now, do you see the problem? So our suspect is Shannon. That she did it. And if she did indeed steal the chocolate, that will have serious consequences. Now, you are all now on jury duty, right? What's your feeling? Did Shannon do it? I mean, look at her. No. So the verdict is not guilty. Well, you don't know, do you? Oh. Is she guilty? Yes. You know who your enemies are, right? Okay, we have some options here. And actually, what we need to do is we need to write a sort of a protocol in the first place. Before we send her to jail, we need to write a protocol. Protocol is always good. What would be our first point on this protocol? What would be the first thing that a judge actually says? What is the first assumption when it comes to such a terrible crime? Sorry?
She's innocent.
She is innocent. You are absolutely right. Not guilty. Yeah? So, we say in our protocol how to deal with this scoundrel protocol. Not guilty. Right? This is our assumption. It is our null hypothesis. We say not guilty. What if we do not agree with the not guilty? What would be the alternative? Guilty. This would be our alternative hypothesis. And these are our two options, at least in England. In Scotland, it's different. Do we have anyone from Scotland? No? No convicted criminals from Scotland? Oh, what a shame. In Scotland, you have a third option. It's not proven guilty, which basically means we know exactly that you did it, but you are just simply too smart for us. We can't prove it. Right? But we are in England, so we go with guilty or not guilty. Now, the jury has basically 4 options. Now, let's go through these options. reality. Not guilty. She didn't do it. Or guilty. She did do it. That's the reality. And we make a judgment. Our judgment is not guilty. That's our judgment. Or we say she is a naughty girl. She is guilty. We don't know the reality. We only make our judgment. And luckily we have the correct verdict in two cases, right? We have not guilty verdict if she is not guilty. This is called a true negative. We also make the right judgment when we say she is guilty when she actually did the crime. So true positive. Yeah. But we have two options where we make an error, where we make a mistake. Here, we say she is not guilty, although she did it. This is called a false negative. Here, we say she is guilty, but she didn't do it. This is a false positive. Yeah? We make errors here. This one here is called a type 1 error and is usually abbreviated by the Greek letter alpha. This one here is a type 2 error and is abbreviated by the letter beta. Now, tell me, which is more serious in this particular case? Alpha or beta? Sorry? Alpha. Why do you say that? I mean, you're basically your ass is on the block, right? You would be seriously hacked off, literally,
Yeah.
if we convict you and say you are guilty, although you didn't do it. Yeah? On the other hand, if we commit a type 2 error, you go away and say, give me more chocolate, right? I get away with it, right? So we need, in our deliberation, think about which error we want to keep as low as possible. If we say we want to reduce the error, the type 1 error, to 0, so we will never make a type 1 error, then we will never say guilty, even if she did it. So by reducing the type 1 error, we immediately increase the type 2 error, and the other way around. So what we need to do is we need to come up with something where we say, we are pretty sure in our judgment. Yeah? But it's entirely up to the jury to set a value for alpha, and this value for alpha would be how often are we actually wrong? How often do we make a type 1 error when we do the judging? That is what alpha tells us. Yeah? So alpha is, as I said, type 1 error. It's also referred to as the significance level. Significance level. It tells us how often we are wrong. Now, of course, poor Shannon has to endure all this abuse. And actually, she didn't totally empty. Okay, so I'll take a couple. Thank you. Big applause for Shannon, who got the abuse from me. So, this significance level alpha that we use is sort of how confident do we want to be. If we say we don't want to be very confident that we make the wrong decision, I mean, nothing will happen to her. She doesn't even get a criminal record or so. It doesn't really matter whether it's guilty or not. Not a big deal. But if her life depends on it, we need to keep alpha, we need to be absolutely sure. And that actually brings us to this whole calculation thing. To change that. We said we need sample size. We need variability. And we need sort of a confidence. How confident do we want to be in our decision? So confidence. Let's call it confidence level. And this confidence level, this last bit, that includes this type 1 error, but we can set it to whatever we want. Bearing in mind, too low an alpha will give us high beta and the other way around. But it's entirely up to us how we want to set it. And for one reason or another, it has sort of, people choose a confidence of 100%, that's the confidence level, minus alpha. We want to be fairly sure, and we set it to 95%. That's the confidence level. How big is alpha? 5%. So we say that our error rate in making the wrong judgment will be 5%. And that's fairly, decent. Only in 5% of the cases we make the wrong judgment. Now, if you, for example, ask my wife, she will say my alpha is around 99%, so I usually make the wrong decision, and but that's normal. But we can set it to whatever we want. if you do, for example, clinical trials and want to make sure whether a drug really works, you say 5% of the times I'm wrong. Now that's not good enough. I want it 1% of the times only being wrong. Yeah. So these are the hallmarks of this confidence interval. And we can now calculate this, what I said, x bar plus minus margin of error by using this information that we have. The margin of error is defined as the standard deviation, the estimated standard deviation for the population, divided by the square root of the sample size times a critical factor. Let's call it critical factor. And this critical factor actually depends on our alpha. So that would be our margin of error. Now the big question is, where do we find this critical factor? Now let's assume for the time being that we are working with a normal distribution. So for normal distribution, let's assume we also know the population standard deviation. We know sigma. Then this margin of error turns into sigma over square root n times the factor, which is called a z-score. And the z-score is a value that contains 95% of the data. How do we calculate the z-score? Z-score is just simply calculated is our observation minus the mean divided by the standard deviation. Looks weird? If we just simply go back to our standard deviation, what we need to figure out is how many standard deviations in our normal distribution, how many standard deviations actually do we need to be away so that 95% of our data are included? Can you? 2, exactly. So in this case, the z-score to include 95% of our data would be 2. So for 95% of our data, this would be 2, this value. So the z-score would be 2, right? Actually, it's not exactly 2. It's just, we work with 2. The more better value, if you like, is actually 1.96. So 1.96 standard deviation to the right, 1.96 standard deviation to the left. That would be the correct value. So we could calculate the margin of error if we have a sample where we know the standard deviation for the population. We can calculate that. Let's say we have this way, that way. Let's say we have just simply sigma equals 10. We have a mean of 50, whatever this is. We have a sample size of 100. Now we can calculate the margin of error. We can calculate to 10 over square root 100 times 1.96, right? So 10 divided by square root 100, what's that? 1. So margin of error would be 1 times, I just do 2 because it's easier, is 2. So my estimate for the population would be the true population mean is somewhere between 50 plus minus 2. So must be between 48 and 52. Yeah? That is my estimate where the true population mean is located. Are you happy with that? In a way, all this, all this fuffing around with normal distribution and things like that and z-score, we usually go for just simply 2 as the critical factor. That includes this 95% being sure. And that is what this is called. This is the 95% confidence interval. This is the equation for a 95% confidence interval. Yeah? Very simple. You just multiply this margin, you just multiply this, where is it? This sigma divided by square root sample size times 2, and you get your margin of error. Hey, cool stuff. But it only works if we know, if we know the population standard deviation. If we don't know the population standard deviation, we can't really use this equation. So close, and yet not right. This only applies to if we know sigma. If we don't know sigma, if we have to estimate sigma from our S, we can't use it because it's no longer a normal distribution. What can we do? I need a new page here. Where is it? So close. If sigma is not known, usually we don't know sigma, we need to take a slightly different approach. We cannot take normal distribution. Not normal. Nothing is normal. Damn it. We still can use margin of error equals. This time we write S. We write square root n. That still stands. We write critical factor. But this time it's not that easy. It's not 2. It might be something else. And this critical factor that we are now using doesn't come from a normal distribution. It comes from a similar distribution. This critical factor still includes alpha of, let's say, 5%, like we had with the normal distribution, but is no longer normal. We need to use a different distribution. We need to use what is called the T distribution. What on earth is a T distribution? T distribution is something very similar to the normal distribution. Let me just see if I find an example for the T distribution. Yeah. T distribution looks pretty much like a normal distribution, like a bell-shaped curve. But it's a whole bunch of distributions. And these distributions depend on the sample sizes. So, got another problem here with sample sizes. We need to get this T distribution, get this critical factor and fuff around, and it's a mess, and God. So the standard normal distribution, that is this black curve here, right? That you see here. And as I said, the T distributions come in a lot of different flavors. So we've got, for example, this purple line here that you see here. That's a T distribution. Or we've got this green line here. That's pretty close to the standard normal distribution. They are all T distributions. Now, for the normal distribution, we would say 2. That would be 95% of the data. But if we want to do that for the purple one, we would need to go further afield and say we need to have the data here around 4-ish or something like that for our critical factor. And what you see here in this legend, there is something weird in it that is called df. What on earth is a df? So we need to take these, I copy that. For the t distribution, each t distribution has a df. Does anyone know what a df is? Can you eat it? It is degrees of freedom. You're absolutely right. Degrees of freedom. Now, what the hell is a degree of freedom? I mean, if we don't put you in jail, this is a degree of freedom, right? Yeah. So that's a good thing. What is a degree of freedom? Give you an example. A plus B plus C equals 10. Can you tell me the values for A, B, and C? To make this equation correct. Can you tell me?
I could tell you some numbers, but I don't know if they would be what A, B, and C are.
So you have no clue?
No.
Okay, good. Say 1 plus B plus C equals 10. Does that help?
Helps, but I still can't do it.
You can't do it. Is that because your mathematical abilities are not?
I could tell you two numbers that add up to 9, but there's a few combinations.
You can't do it, right? Okay. 1 plus 4 plus C, no, 1 plus 5 plus C equals 10. Does that help?
Yeah, 4, I think.
You're absolutely right.
No pressure.
Yeah. How many numbers did you need?
2.
That I give you?
Oh,
2.
Yeah.
Yeah. So I could choose 2 numbers, and the last number you figured out yourself.
Yeah.
Yeah. So this equation here, people say this equation has 2 degrees of freedom because I could choose 2 numbers and the rest you could figure out yourself.
Mm-hmm.
Yeah? So in our case here, we had n variables, which means n minus 1 degrees of freedom. That's all to it. That is what degrees of freedom actually mean. So when I have here 1 degree of freedom, it means my sample size is actually n equals 2. N minus 1 gives me the numbers of degrees of freedom. So if my sample size is really small, only 2 people measured, then my distribution, this t distribution, is this one. And in theory, I could easily look up how much I actually need for this. I think this is actually around, can't remember, it's over 6 or something like that. So I would have to multiply this number that I get here, this s over square root n, I would have to multiply that by a rather high number in order to get the margin of error. Yeah? Actually, this s over square root n has a specific name, this term, so that people don't always have to say S over square root n. You mentioned it today.
Yeah, standard error.
This is the standard error. Well, sort of. This is the standard error of the mean, abbreviated SEM. Yeah, standard error of the mean. You can have other standard errors, not of the mean, calculated in a slightly different way. So what we can do now is, if we knew our critical t factor, and I write that down again, so we would get x bar plus minus s over square root n times critical t factor. And this critical t factor depends on degrees of freedom, and it depends on our significance level alpha. Then we can find out what is roughly, where should the mean of the population, where we think is the population mean located. Somewhere in there. We are pretty sure that it's there. We could be wrong, right? We could be wrong. We will be wrong in about 5% of the cases, but we can calculate, we can give at least an estimate where we think it is. And that is what is called the confidence interval. And in our case, the 1 minus alpha confidence interval, in this case, 95% confidence interval. We could identify, say, a 99% confidence interval where we are even more sure where the true population mean is. We can say it doesn't really matter. We can define an 80% confidence interval. It's entirely up to us how we deal with it. Yeah? So that is confidence interval. And you are probably totally sick of all these calculations and the weird concepts. Luckily, there is a beautiful online calculator that can do that for you, these confidence intervals. Let me see if I've got that somewhere. Let's say we've got a data set here. This could be, for example, the diameter of a tumor or so in micrometers. Just to give it a clinical touch. And what we can do is we can say, right, at this stage in the life of a patient, we've got 1, 2, 3, 4, 5, 6, 7, 8 patients. We want to calculate what is the true population mean of this particular tumor. We cannot measure all the patients, but we can try to figure out what it is. Roughly, we can say we calculate the mean. I think the mean is about 58.2. I've done that before. Plus, minus this margin of error. And would be good to see this margin of error now. And if I am not mistaken, I have the QR code for this for an online calculator. Let me see. If you scan this, you should come up with an online calculator, and I need to say a little bit about that. Does it come up with an online calculator?
Yeah.
Yeah? I just want to give people a little bit of time. Everybody got it? I'll put it also on the Research Skills website. And let's go to that. So what you want to do is you probably come up with, that's not what it looks like, does it? It comes up with this one. Is that right? Yeah. This is a calculator for something else that we are going to use. But what we are looking at is the two-sample t-test here for the time being. We will talk about the two-sample t-test. And all you need to do is, I just remove this side here. Should not have done that. What you see here is that the calculator will, I just leave the data on the left-hand side of the calculator. These are the data actually from our tumor that I've put in. And it will calculate a confidence interval for this sample. This is the sample here. It will calculate 58.175 plus minus 23.4. That is our margin of error. This calculator automatically calculates this margin of error from all the information, from the sample size, from the estimated standard deviation of the population, and from this critical t-value. And it even calculates the lower and the upper bound. So basically it calculates 58.175 minus 23 and plus 23, and it gives you the lower and upper bound for your confidence interval. So this means that with this tumor, we can be fairly confident that the true population mean is somewhere between 34.75 and 81.6, basically. There, somewhere in there, we are pretty confident that the true population mean for this tumor is somewhere there. That is basically what this confidence interval tells you. Does it make sense? Lots and lots of faffing around in the second session when you couldn't have it so easy with this calculator. But I wanted to give you a good understanding of why we are doing things. What are these different concepts that we are looking at? Yeah. Thank you very much. I think we call it a day. Tomorrow, we are looking then at our protocol again in order to figure out what happens to Shannon with our hypothesis testing, because we still haven't finished that. And what we can actually do with these confidence intervals is quite cool, because we can use these confidence intervals to compare two samples with each other. and say, for example, does a drug work or not? We'll see. Thank you very much. Any questions? When is finishing? Now. Go in peace, but please go.